Simple pendulum. A simple pendulum consists of a mass at the end of a lightweight cord. We assume that the cord does not stretch and that its mass is negligible. In order to be in simple harmonic motion, the restoring force must be proportional to the negative of the displacement. Here, that force will be minus mg sine theta, which is proportional to sine theta and not to theta itself. Now you're going to ask, where did that come from? Well, this is more an AP1 problem than an algebra-based physics problem because you have to do some trigonometry. But let's just do it at a high level, and when you take the next course, you'll figure out exactly how it works. If you pull a pendulum bob up, right, you're pulling it up that way, you're displacing it x, where x is going to be tangent to the circle there. The only force operating on that pendulum bob would be gravity, which is pulling it straight down. But not all of the gravity is making it move left to right, just a piece of it. So you would resolve gravity into two pieces, mg cosine theta pulling it this way, and mg sine theta, which is perpendicular to this guy, who is making it move up and down. Okay, so don't worry too much about this. It's just we're teaching you something a little ahead of the time. But the problem is sine theta is not equal to x. That's a sine function. But we don't have to worry about it if we just pull the pendulum up on a smaller angle, somewhere less than 15 degrees. In that case, and here's another bit of trig, sine theta is almost equal to theta when it's expressed in radians, and x, you take a triangle, will equal L theta. So we'll replace sine theta with x over L, right? You just say theta is x over L, and now we have the force is roughly equal to that. So what's that telling us? Well, let's wait on the next slide. This is a pretty consistent physics trick. We have this equation here, and look, we know what F is. We like negative, and x, that looks like Hooke's law, right? F is equal to minus kx. So that works if we say k is equal to mg over L. Now, we know the period of a mass oscillator, and now we're just doing math, not worrying about whether it's a pendulum or an oscillator. We're just looking at the math. And so this k here, we're going to replace it with mg over L. That's this. We do a simplification, and we get t is 2 pi times the square root of the length of the pendulum divided by g, and the frequency is the inverse of that, 1 over 2 pi square root of g over L. Big deal. M canceled out, so the mass doesn't matter. A simple pendulum with a length of 2 meters oscillates on the Earth's surface. What is the period of oscillations? Our givens, 2 meters, and g, you're on the Earth's surface, so little g is equal to 9.8 meters per second squared. We use our period equation here. We substitute in the givens. Here's g, here's the length of the pendulum. Pi is roughly 3.14. And we get a period of 2.8 seconds. A simple pendulum with a length of 2.60 meters oscillates on the Earth's surface. What is the frequency of the oscillations? We will use the frequency equation, and notice in the givens we weren't given the mass. That's because you don't need the mass. You can have a 2 kilogram mass, you can have a 0.2 kilogram mass, and you'll still get the same frequency for the same length of the pendulum, and assuming you're on Earth where you have a gravitational attraction of 9.8 meters per second squared. Substitute in the givens, gravitational acceleration up there, length of the pendulum, 1 over 2 pi, and we get a frequency of 0.3 hertz. The two types of energy in a pendulum are, this time instead of elastic potential energy, we have gravitational potential energy. There's no spring involved here. It's just that the pendulum bob goes up and down and it changes its GPE. And again, just like the mass oscillation system, the mass spring oscillation system, we have a kinetic energy. At any moment in time, the total energy of the system is constant and comprised of those two forms. So total mechanical energy is GPE plus KE, or mgh plus 1/2 mv squared. Total mechanical energy is constant. Example 1, energy of a simple pendulum. A mass of 0.50 kilograms oscillates on a simple pendulum with a length of 1.5 meters that reaches a maximum height of 0.080 meters when it is in simple harmonic motion. What is the maximum gravitational potential energy? And we'll work the answer on the next slide. As always, first we'll write out our givens. We've got the mass, we've got the value of g, we've got the maximum height of the pendulum swing, and we've got the length of the pendulum. The gravitational potential energy is a maximum when the pendulum reaches its maximum height. So we set GPE max equal to MGH max. We substitute in the givens, carry out the math, and we get the maximum GPE is 0.39 joules. Example 2, energy of a simple pendulum. A mass of 0.50 kilograms oscillates on a simple pendulum with a length of 1.5 meters that reaches a maximum height of 0.080 meters when it is in simple harmonic motion. What is the maximum kinetic energy? We write out the givens, and these are the exact same givens as the previous problem, example 1. The total mechanical energy, TME, in simple harmonic motion is conserved. Therefore, the maximum kinetic energy is equal to the maximum gravitational potential energy that was found in the previous problem. So our total mechanical energy is equal to the maximum kinetic energy and also the maximum gravitational potential energy. Since we already found this value, which was 0.39 joules, that is also the maximum kinetic energy we can have. And we have that when the GPE is 0. A mass of 0.50 kilograms oscillates on a simple pendulum with a length of 1.5 meters that reaches a maximum height of 0.080 meters when it is in SHM, simple harmonic motion. What is the maximum speed of the mass? Finally, we will use the kinetic energy equation to find the maximum speed. So we have the maximum kinetic energy is equal to 1/2 mv squared max. So solve that for V max. So you take a few steps, but this is the answer you'll wind up with. You multiply both sides by 2, divide both sides by m, and then take the square root of both sides. Then we substitute in our numbers and use kinetic energy max, which is equal to 0.39 joules. That was found on the previous slide. Carry out the math, and we have V max is 1.25 meters per second.